page 79. Let's get that rocking. Whoops, not that. This one. Okay, this is a classic. The whole point of this one is to do a demo. And if you have a spool of thread or at home, well, it's a tough demo to do unless you have the following. So if you want to understand this demo, you need a significantly different radius for the central spool versus the outer spool versus the outer radius. So you need R inner and R outer to be significantly different. So I don't know if you have that, but if you do, you can do this one. The whole point of this problem is this. We know that if this thing is rolling, you could consider the instantaneous pivot. And notice, depending on which way you pull on the string, this one has an R vector this way. It causes a torque that direction. This one has an R perpendicular this way. And so notice this causes a torque that way. And this one, the line of action goes through the pivot. There is no torque. There is no rolling motion. This one slides. It's very cool. So it's a lot cooler in person, but this is what we've got right now. So if you want, you can try and get a spool and try and do that, but I don't have a way to do that right now. So depending on which way you pull on a yo-yo, it will roll towards you, away from you, or it won't roll at all. It'll just slide. Obviously, this one is the hardest to do because it's hard to get this to line up perfectly. All right, so clear that. That was that. All right, that's a cool demonstration. If you want to do the geometry on that, you could actually figure out the angle using this question. All right, 10.63. 10.63 is a classic question. You should definitely do this one. It's classic. All right, so the idea is we did this before. However, before we said it was sliding. Now it's going to roll, not slide. And what should that do to the problem? Let's think. If you have a problem where the ball is rolling, okay, some of the gravitational energy is going to go into translation and some of it is going to go into rotation. Because some of it goes into rotation, this should have to be raised up a little bit higher than the sliding case. So if you look back at the sliding problem, which was 8 point something, I'm finding it really quick, 8.4. You can compare it to 8.4. Now, when I see this speed, immediately I'm thinking, do an energy problem. Do an energy problem. And then, oh, losing contact. Hey, losing contact. Immediately you're thinking set n equal to 0, right? I hope. Okay. Oh, yeah. And then we just kind of address this one. All right. All right. That's pretty good. So that's 10.63, just some notes on that one. 10.64, this is a pretty good one for just getting used to some numbers and such. So, and again, notice I said total kinetic energy. That's a giveaway. If you're talking about this, you know that there's a 1/2 mv squared. But then there's also a 1/2 I omega squared for each wheel. So there's probably 2 of those and the 2 and the 1/2, right? Because there's 2 wheels. So it's just making sure when you say kinetic energy, remember that now kinetic energy is not just 1/2 mv squared. You also have to consider if there's an I omega squared in there. Okay, so when you see kinetic energy with rotation, don't forget this crap. All right, let's scroll down. This one is a good review to see if you learned some of the things that we talked about today. 10.65 addresses some of the things about that instantaneous pivot. So it's forcing you to state what facts are there. So, and this is pretty cool. And this is another, basically a variation on this one. So these two are very similar. This was an old test question right here. Take this, this is a concept question. So let's take the second, see if you can actually answer this right now. You got a solid sphere, it rolls down and it takes time 1 to roll down. So that means here, this one took time 1. Great. Now, Angus drills the hole because he got a free energy drink. Yeah, and they can complain about Jorstad. That would definitely make me get the work done. So this time it takes time T2. All right. My question is, I guess, which one should get down faster? So let's just do this, or which one takes longer? You had the original one. Let's say this was mass M. This one would be M minus a little bit. So there's actually less mass here in the second one. And so, okay, so Nick's pulled in with his shot here. He thinks T1 should be less than T2, and I agree with that. I know this is going to sound a little strange, but when I look at this, I think this one is a figure skater with her arms in, and this is the same figure skater with her arms out. The mass is distributed farther from the axis. So if you think about the axis in each of these, in the solid sphere or the solid one, the mass is closer to the axis. And remember that mass doesn't matter in this problem. That's a decoy. All right, let's clear it and move on to the next one. All right. Ooh, regarding question A, this is something I want you to think about. Look at this. Blah, 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 this one. As soon as you see this, what should you be thinking in your mind? What type of problem are you going to have to do? Kinematics. Hopefully that's what you thought. We'll check the chat. Yep. So that's a good sign. So this is one where you could do energy and kinematics, or you could see that at some point, this actually goes to a question Jay asked earlier, which technique is the best? You got to know all of them, because this one is impossible to do without kinematics. Kinematics is our one method we have for getting time involved. All right. Oh, I love this one. 10.67. Take a second to read this one. 10.67. Identical discs, identical force, aerial view, you're viewing from on top. They're like hockey pucks or something. String pulls one of them to the right, and it's going to accelerate. Now, in the second case, we're going to pull on the string, but it's going to spin. Which one should accelerate faster? 1 or 2? Don't look at the answer. Take your guess. Okay, so they have the same mass. One of them is being pulled with a string that's wrapped around it. Let's see what we see. Same. Don't overthink it. They have the same force, they have the same mass, they have the same acceleration. And if you don't believe me, this is one of the few I found a video for. Oh, I didn't link to the video. Oh, crap. Oh, here it is. Oh, whoops. Whoops. I love it. World Wide Web for Two Pucks demo. If you do a search for Two Pucks demo on YouTube, I think you're going to find this. So let me just see if I can do this one. Maybe it had to be one word. Sheesh. There it is, right there, this one. Okay, so you guys can watch that later. All right, I'm not going to show you a video over a video. That would make me barf. All right. Yeah, all right. So isn't that wild? Yeah, and so the idea, now, you don't get something for free. Think about the energy involved. Clearly, if they both are translating at the same rate, the one that's rotating has more energy. So how does this work? The trick is, if you're going to pull with constant force on a string that's unraveling, you're pulling really far because the string's so you're actually pulling a lot more string. You're doing a lot more work. And so that's why it has the same kinetic, same translational kinetic energy, but has also the extra rotational. It's amazing. And it was Two Pucks demo. Yeah. No, this is an aerial view. So if you go back and look at it, it's one of my favorite ones. So think of the figure as being a view from above of two discs on a perfectly smooth hockey rink. If you want, this relates to some of the required questions. Whoops, those are the 1040s, I think. Where the heck is it? Look at 1040 through 1042. If you haven't done them, they're on the required. So I'm going to put them in there. They seem deceptively easy and simple, but you've got to do these problems. 1040 through 1042. It's in the required problems. I do think it locks in the concept that is easily confused that we just saw there. All right. So, all right, let's move back into there. Isn't that a fun one? So trippy. Oh, there's a question. Okay. Yeah, if the same amount of work was done, clearly the one that has rotational and translational would not be accelerating at the same rate. In order for the same work to be done, however, you would have to apply a smaller force to the one that is unraveling. Just think about it like this. If you were walking while pulling a string, if it's tied to the center, you'd have to walk at one rate. But if you want to apply the same force, you'd have to be running to apply the same force to a string that's unraveling. Otherwise, the tension's going to go down. So you can think of this as you're pulling it along while you're running if it's unraveling. All right. Yeah.
I've got a question for you.
Yep. Go for it.
Looking at 10.67 again. Initially, I was looking at it from a different perspective. And then once we talked about like it being on a ice rink and whatnot, it made more sense. But I was imagining the same problem, but this being a side view and each object sitting on, it's like a puck, but it is rolling on its side on a just a flat table, something like that. So does it change?
Would that look like this one? More like this?
Yes, it would.
Yeah, and notice that's a challenge problem. So these are totally doable.
Oh, yeah, that's not in my book. Okay.
Oh, you lucked out. But so, or like this one here. Yeah. So these ones all get kind of crazy. And some of these are really weird. Okay, I got to show you one of these. I forget which one it is. I forget which one it is. Friction is actually in the same direction it's moving. Yeah. This is crazy. Let's go look at here. Whoops, that's a different one. So look at this one. I'm looking at 10.69 really quick. This is a challenge one, so obviously you don't have to do it. But if you want, you can actually follow this. It's nothing that crazy. But look at this. I don't know which way friction points, so I'm just going to work it all out. I did all the math. And notice friction turns out negative, which means friction is actually pointing the other way on this one. So in this particular problem, you pull it to the right and friction points to the right. Isn't that crazy? I mean, that's crazy. I love it. I love it. Anyways, all right. Yeah. Let's see. Yeah, before the plague. Yeah, back when we could do demos in class. It's pretty fun. Yeah, there's some really interesting stuff. So I'll be honest with you. I really love problems 10.69 through 10.72. Why else would I do them knowing that I'm never going to make my students ever do those? So if you're into mechanical engineering and this kind of stuff, you might find those problems interesting afterwards, but they're really neat, really amazing. If you're a physics major, 10.70 relates to a skill used in an advanced physics class. And yeah, so they're all in there, but boy, trying to do those problems is it's pretty gnarly. So I would skip it, especially in this semester. And maybe if you're bored this summer, stuck inside, then do every other problem. All right. So let me see. Okay, I'm going to start showing random test questions, and then you don't have to respond in the chat, but I'm gonna show you a question at random and see if you can identify what technique to use. All right. So it's just rapid fire. What technique should you use to solve the problem? So I'm gonna get a couple of problems up here. Let's see. Let's see. Oh boy, a lot of windows here. Let's go back here, go back here. All right, so let's start out. Oh, let's go here. All right, so again, what are we trying to do here? It's not do the problem, it's identify the right technique. All right, so take a look at this one. And think to yourself what type of problem it is. And I'm going to bring up a little clock on my screen here. So I'll give you 30 seconds and just figure out, just try to think to yourself, what would I do if given this problem? All right. And so hopefully you thought the following. This looks like problems with masses, acceleration, and force. I'm going to draw an FBD, write some force equations. Now, wait a minute. It says block M does not slide downward. When I see block M does not slide downward, I can do a system FBD. So I could do one FBD for that whole blob up there. That's what I would do. Forces, FBD, force equations, solve for something. Next. Okay, blah, blah, blah. That's a concept question, whatever. Let's look at this one. A ball, mass M, supported incline wall, frictionless, sweet, normal. I hope you see what to do right away. I'll pause. All right. Hopefully you thought, wait a minute, this is a force problem too. There's a normal force here. There's a normal force here. If you haven't remembered this, but normal forces point perpendicular to the surface, there's also an mg down right there. So we could call this normal force 1, normal force 2, and mg. Piece of cake. Next. All right. Ooh, I see a problem with a spring and a block. My first gut, oh, well, I'll let you think. I'm going to check the chat. Okay. Okay, so you guys, okay, so I'm totally lost when you're doing this one. Usually spring problems are energy. When I see a spring, I'm usually thinking energy, not always. We'll see the exception soon enough, but let me see. Oh, speed. Speed is an indicator I should do an energy problem. Spring is an indicator we might do an energy problem. Release from rest. I'm going to write down the energy equation. Wait a minute. Friction. Oh, negligible. Sweet. If we have friction negligible, there's no work done, right? All right. So that's gonna be pretty easy. Let's see. Do you need a force equation to solve for the spring? I don't think so. In this case, this one would be, I could just do this one really quick, right? Let's see. Released from rest. So K initial equals 0. So I get M G. It follows a short distance X sine theta. Right? Because this one is up in the air some distance X. If this one's up in the air some distance X, this one's going to fall some distance X. I hope you've seen me do this trick a couple of times now, where if you have something that's stretching on an incline, the distance it stretches here is the same as the distance it stretches here. 3mgx. That's the initial gravitational. We'll call that U initial for gravity. Now, initially unstretched. Friction is negligible. Done. We've done the first side. This is the initial energy. At the end, you have 1/2 m plus 3m v squared. Why? Because m and 3m are tied together with the string. So that's why they're moving at the same speed. It's an inextensible string. All right. And so now wait, after it falls, all the gravitational energy is gone, right? Because this one, if I could, it's like saying this one is back down to 0. And then this one, y final is 0. So y final is 0 for both of those. So now we get a 1/2 kx squared, and I think that's it. Piece of cake. All right. And I'm going to get to the chat and see if that made sense. Yeah. So Nick asked a really good question. And this is what I've seen a lot of times. People try to use the spring force on this problem. And that's a horrible, horrible, horrible way to do it. The reason that's horrible is because the spring force changes. The spring force is not constant. So don't use forces at all on this type of problem, okay? If the spring changes length, the spring force is changing. It's a variable, right? If you stretch a spring a little, that's a lot different than if you stretch a spring a lot. Okay, because the force is not constant for a spring, you could use forces, but it would be very hard and it's not recommended. Most students get it wrong. All right, hopefully that addresses that one. Okay, that's just a fact. See if you remember that fact. All right, let's take a look at this one. And let me bring up my clock. Potential energy versus position. Got it. Okay. I'll give you a couple more seconds. I'll even scroll down a little bit. Hopefully you identified this one as our plotting type questions. Jay, you missed one there. It's also up here. So hopefully you're remembering this is, you just have to know your graphing rules for potential energy. So remember that force relates to the slope. Force relates to the slope, and there's two regions here. No slope, no slope. That's your deal. And if we go to the equation sheet, That's the equation. Your new equation sheet looks a little bit better. That's your equation. Force is the derivative of u, and likewise, u is the integral. Delta u is the integral. All right, and I see there's some chat there. Force to the left, that's when you got to remember, which way does a marble roll? Okay. If I put a marble on this thing, if I put the marble over here, come on. If I put a marble here, it's going to roll to the right. If I put a marble here, it's going to roll to the left. This is the force to the left between 1 and 4. Let's get that chat. Okay. So remember, neutral. Okay. So good questions, all of you. Let me clear these out. So remember, this is stable. A marble rolls back and forth in there. This is unstable. Whichever way you go, it leaves forever. This is called neutral equilibrium. If it's rolling to the right, it keeps rolling to the right at a constant rate. It's dynamic equilibrium. If it's rolling to the left, the marble keeps rolling to the left at constant rate. All right. So there's that one. Oops. Let's keep going down. Okay. When it's at 2 meters, okay, so this is going to relax. Okay, so when I'm at 2 meters right here, let's see, I started at 3 and it's moving to the left. So I started here and it's moving, so it should be speeding up there, right? If it's going downhill, it should be speeding up. So that's it, nothing fancy there. Yep, okay. And then the speed, here you do what type of problem? 4D, what would you do? Think to yourself. We're trying to find the speed. Here's the original problem statement. I would do energy problem. The change in kinetic energy is opposite delta U, or K initial plus U initial equals K final plus U final. I'm going to check the chat real quick. Yeah, okay, good. Yeah, kinematics would be bad, right? Because with these energy problems, you don't have constant acceleration in most of them. Some of these, I think, Nick, these would have been the rare exception where you could have used kinematics. Look at that problem again. In this case, because, look at this, constant slope, right? That means force is constant, which in turn tells you that A is constant. So in this rare case, you could have used kinematics. In general, bad idea. Energy always works. Kinematics only works if the slopes are constant. Okay. So you would have been fine in that case. All right. Everybody, I think this is helping, right? Is this good? If so, I'll keep doing it. If not, I'll do something else. Okay. Okay, got it. All right. It's not constant for the whole graph, Sean. You're right. So going back to Sean's, you're right, Sean. So what you could do is you could use constant acceleration for this section, and you would know if it starts right here at 3 and ends up down here, you could see that delta x is something like -2, because it goes from x equals this to x equals that. This is what's weird about these graphs. You have to think about the marble rolling left, right, but it's as if it's going on this track. It's not really going up and down. It's basically going purely left, right. So if I go from this x coordinate to this x coordinate, my delta x is -2. And then at that point, you'd have it'd be a two-stage problem, Sean. So then here you'd say A equals 0 because there's no force. And then you could do just delta X equals -1, and you'd know VT equals -1, something like that. Sean, hopefully that addressed your question for this one. In this weird case, yeah, you could do that. Oops. Hey, this one looks familiar. I told you I got all my workbook problems from students failing test questions, right? So that's why the workbook looks a lot like these tests. It's because these were originally not in the workbook. And then when students didn't get them right, I added it in. Let's read this problem. All right. So I want you to think to yourself what type of problem this is. Hopefully you got it. I'll start drawing. There's a normal force, mg. And should these balance? Should these be balanced? No, because it's got to accelerate towards the center of the circle. Now over here, whoops. This is where it gets crazy, right? There's mg down and the normal force up. For this problem, this person is going at constant speed. So obviously they're hitting the gas and the brake as they drive over these hills, but right at the very top, there's no forces left or right. Well, there's no net force. Obviously there's a force from the car pushing it forwards on the road, right? So if the car pushes backwards on the road, by Newton's third law, the road pushes forwards on the car, and there's atmospheric drag pushing back, and those balance out. So technically there are some forces left, right, but they balance. So there's a frictional force forwards on the car from the wheel trying to twist backwards, and then there's drag. But we don't need those forces because these two cancel out. They're equal and opposite. How do I know? At constant speed, A tan equals 0. All right, and so notice in general, if you're accelerating towards the circle, here this force is larger, and over here this force is going to be larger. And I'm going to check the chat, see if that helped or hurt or whatever. Yep, force equation, basically straight force problem. Forces with circular motion, and you're supposed to remember, oh, AC isn't equal to 0. All right. I love to do questions about work on the exam that look like this. So kind of conceptual. You remember chapter 7, we didn't spend a lot of time in it. So these are how I try to get that involved. So here I ask about a normal force. And so that one, I guess you just think about it. I'll give you a second. And I'll scroll down just a tiny bit. So think to yourself. Something like that, yeah. Basically, this is what I'm thinking of. Moving downwards, speeding up, that means acceleration is down. There's a normal force up, mg is down. And then we also know it's moving down, right? So if the normal force is up, actually the acceleration is a decoy. This is displacement. Because normal force is opposite displacement, negative work. So I'm just checking Ryan's question really quick. Correct, Ryan, correct. All right. Now, in this one, constant speed, that tells me that delta K equals 0. But who cares? Is the gravitational force doing work on the boy? You bet. Right? So if you view this, here's a box, here's a slide, right? There's a normal force, there's mg, and then there's friction. Right? If you're going downwards, if the displacement is downwards like this, there's a component of mg that goes that way. This would be positive work. That's it. Notice in this particular problem, if you want to go here, the normal force is 0. The work done by friction will be negative. The work done by mg is positive. So remember, gravity can do positive work if you're going downwards. Let me check the chat. Yeah. So Jay, in the first question, it doesn't matter what acceleration is. A could be plus, minus, or 0. As long as moving down and normal force up, work normal equals yeah, it's all about the displacement. So that was a trick question. The acceleration has nothing to do with the sign of the work. Yeah, now obviously, if you're accelerating in a different way, that would have an effect on the FBD, agreed? So if you were accelerating upwards here, then you would be slowing down, but you're still moving down. As long as you're moving down, it doesn't matter whether you're speeding up or slowing down. Yep, that's a tricky one. And that was the whole point of that one. Hopefully that was kind of fun. Okay, let's keep going. All right, you should know this right away. What do you think? There's a reason this was right after a circular motion problem. You can go around a circle at constant speed v, and you need a force towards the center, like tension. There's the counterexample. So constant speed in one dimension has no net force. So in 1D motion, when we were doing chapter 2, we could do those back and forth all day long. All right, let's keep going. Hey, I think you know that one. Looks like a force problem. When you see tension, you're like, yeah, I better do forces. Hey, people, don't forget, on your equation sheet, you know that A equals if you see omega in the question, you might want to use this for AC. If you see V in the question, you might want to use that for AC. Okay. Okay. Yep. Okay. So every test is different. And so, yeah, it looks like this one had quite a bit of force stuff, but yours is not going to be the same distribution. So let's take a look. If I show you just one, it's never good. You know this, right? So you know you have to look at multiple practice tests. So let's see. All right, that's fine. Let's go back and look at another one, right? Or let's just go to here. Oh, wait, where was I? Oh my gosh. No, not that. You also have some of these ones, right? So let's go to here. All right, now remember, some of these questions are not for you. Take a look. Let's see if you think this question matters. Think about what type of problem this is. Hopefully, when you see these words, you're immediately thinking, what concept? Momentum. All right. So answer these questions to yourself. Same force magnitude. I should have put the word magnitude in here. So in this case, the smaller mass. And what's so counterintuitive about this is the fact that they have the same force, the same change in momentum, but because one of them has a much larger mass, we don't notice it. Big objects don't have a noticeable change. So like it slams into his face and stops, but in reality, what's happening is his face slows down a little bit too. Tiny, tiny bit. Okay. I'd like to see the demo where the taco is thrown into my mouth and then I eat it. Yeah. Oh man, I'm hungry right now. Okay. Oh yeah, so the question, this is good. So yeah, I posted the list of problems from chapters 9 and 10. So if you want to look at those practice exams, let me make sure I can find those for you. I think it's in here somewhere. Oh my gosh. Where were those? Was that in an announcement? So I'm looking for those links, the problems. Oh my gosh, this computer. Practice exam breakdown. Oh my gosh, this is so bad. There it is, right there. All right, so I'm getting out of that really quick. Okay. Yeah, it's in there somewhere. Yeah, hard shell. True, true. That's why I go with the double stuffed or whatever. Yeah, it's in the announcement. So if you need the problems, all right, there we go. So there's that. All right. Let's see if we can get a couple more problems in. All right. I love this type of question. You can take a look at it later. Ooh. Take a look at this one. Hope. Okay, I'll let you read. Nope. Right? Can't use kinematics. Swinging motion is the one where you can't do that, right? That's true initially. So that's the initial alpha. Alpha initial equals this garbage. But alpha final equals 0. Alpha is not constant. So this is not valid. That's why that fails. All right, that's cool. This one, straight center of mass. Oh, whoops. I guess I just looked at it and I saw it and knew it. My bad. I gave it away there. I'm getting tired. I'm just answering the questions. I see density. As soon as I see density, I'm thinking, oh crap, I need dm. In this case, I use the symbol mu, so it's mu dx. And then you do the integral, n comes out in the exponent, and you solve for it. Let's see, either 2 or 1d. Yeah, something like that. Yeah, that's pretty close, Phil. And then often if I do uniform, I'll put a hole in the object. That's right. So basically, you're going to get something like either this or something with a hole in it. And I won't tell you which one. So you got to study both. That's basically it. So just know both. Yeah. And I think hopefully you're getting a little better at that. Hey, try this one on. Uh, yeah. So I guess I hadn't really worried about that lately because I was more just trying to get through lab. So maybe I'll worry about Sam's question after we get through lab tomorrow. All right. Um, I got to be honest with you. I think if you have to use the book, you're screwed. Because if you're trying to use the book, you're going to spend so much time looking stuff up. You got 15 questions. You've got to do you've got 12 minutes per question, something like that. Right now, some of them are conceptual. They'll be literally 1 or 2 minutes. So there's probably going to be a number of questions where you just have to get it in 20 minutes. And yeah, see, that's the thing is if I go open book and then I let you use the workbook and the solution, there's just so much benefit to having the solutions. I don't know, right? Because it's like, man, I've done so many questions that look so similar. That's my main issue with letting people use the workbook and the solutions. So if I did let you, I was thinking about maybe just letting you use a textbook, but then at that point, it's like you're better off just knowing this. Trust me. And even if you could use the workbook, I worry that if you start trying to use the workbook, you're just going to be slow. You've got the same equation sheet. So prepare, at least for now, as if you don't get anything. And then worst case scenario, you'll get something. So if you do forget 1 or 2 things, maybe you'd look it up, but prepare as if you don't get any book. All right. At least for right now, that's what we'll go with. All right. When I look at this one, look at that. This line says kinematics, right? And then you could either use energy or torque. I think I probably would go with torque. I don't know why. The reason I would go with torque on this one is it's such a simple torque problem, right? Here, well, I don't know. Maybe I better be careful here. If you use this one, right, there's a force mg, there's a tension T, but watch out. If this is accelerating down, T is not equal to mg. That's what everybody does. Everybody always says, oh, tension's mg. Seriously, this thing's accelerating downwards. You're going to tell me the upwards force is the same size as the downwards force? That's what drives me crazy in this problem is people always say T equals mg. Shoot me now. Anyways, great to know this is all live streamed. Let's check the chat. All right. So center magnetic sheet. I think you mean the moment of inertia. You get the moment of inertia chart, right? If you look at these, I'll show you that in just a second. Yeah, trig identities, you know the basics, sine, theta over cosine, and yeah, it's just a normal test. Don't freak out. It's a normal test. And no, you're not going to use your own notes or anything. So just treat it like a normal test. Think of it as a normal test. All right. Yeah. Okay. Yeah, look, so you know the exam equation sheet already. I gave it to you a month ago. So, and it makes sense that you guys are asking these questions. You're just nervous, right? But oh my gosh, really? That's still on there? Where was it? Was it here? Right. You can look at this. The test equation sheet has been given to you since there. You get all this, you get all that, right? So that's what your exam equation sheet looks like. And it's like once you have that, it's You don't really need anything else. Yeah. Yeah, exactly. You get this extra one too. Yeah. So you guys are still sitting here 2 minutes after class ends. You're probably going to do all right. So you got to take a deep breath and know that you're right. You can also have some chance to get points during the oral exam, which, yeah, you'll be all right. Absolutely. Yeah. So you might need to do the integral, which is right there on the equation sheet. There's the parallel axis theorem. I mean, it's all there. This is the perpendicular axis theorem. I even gave you that. So it's like, you got it all. Yeah. Yep. 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 I agree. Yeah. I mean, you guys were just answering some of the questions I just asked pretty well. So, I mean, yeah, I'm not going to be easy on you, but I'm not going to be unfair. And when you look at these questions, if you've done the work, you're going to look at them and immediately know exactly what to do. And you will start doing it, especially if you go through at this point, if you've done all those problems already, it's more about identifying what technique to use and not going down a wrong path. And then obviously good time management. It's just a normal test. So yeah, I think you're going to rock this. All right. So Sam, there might be something like that. We'll see how it goes. What will probably happen is if you get the problem wrong, and it happens to be the one that I decide randomly to quiz you on based on whatever, then you'll get a chance to say, oh yeah, this is what I screwed up here. And then you can still get the oral exam points. So remember, the oral exam is worth about half, and the regular part is worth about half. So your ability to respond to the questions will be fine. And like I said, in a similar experience, I think Professor Youngblood said that nobody went down, but nobody really went up that much. So yeah, he said, I think 3 people went up a little bit, but maybe I'm misremembering. But yeah, so just treat it like a normal exam. You're going to rock this thing. Yeah. All right. I think we should probably call it a day because I got this fish burrito here, and it's looking pretty good. A lot better than this chat anyways. So I can at least